Take a look at this sample. I'm actually holding a piece of the mantle, and you can see that the mantle's green. If you were to take this class, of course, face-to-face, you'd get to hold a piece of the mantle too, but we have to make do as best we can being online. Welcome to today's lecture. It's on Earth structure. We're going to be going over the mantle, also the core. I actually have a piece, not of our core, but I have a piece of a core of another planet, actually. And there it is. I actually have two pieces, okay? Those are the cores of other planets. Oh, you can't see both of them. They'd probably just look like little pieces of metal to you. But if you were in the class face-to-face, you'd get to touch them and feel them too. Now, how is it that we've never been to the mantle, yet I have a piece of the mantle, and we've never been to the core of another planet, yet I have a piece of the core? We'll talk about that a little bit later, but maybe something for you to think about, try to guess about before we get to that. So we are going over Earth structure today. I will pop up the lecture here for you now so you can see it. And I should be now in the corner, and you're looking at the Earth kind of split up into four shells. Okay, so these are the four main shells of the Earth. So we're going to be going over Earth structure, the basics of Earth, so that we can get ready to understand the evolution of Earth over the last 4.5 billion years. And of course, that is the answer to your first question, your lecture assignment. Hope you have your lecture assignment up in front of you. I know that I have mine. Actually, I should pull it out right here. Here it is. Here's my lecture assignment packet. Oh, it's stuck up here. There it is. So it's the orange one right here for Historical Geology. And how old is the Earth? The Earth is about 4.5 billion years old. So that's what we are going to be talking about. How did Earth, of course, in this class we study, how did Earth come to be over that 4.5 billion year time period? So let's go over each of these shells. We have four shells right here. We're going to cover each of them in turn. We have this layered structure, kind of reminds me of a nesting doll. If you know those like Russian nesting dolls, it's a little bit of a similar concept, right? Other people maybe think of an egg or an avocado or something like that. And we'll go over each of these layers, okay? So the first one, very simply, is the crust, okay? The crust is what you live on. It's what you are used to. And it's only really very paper thin. Think of, again, the skin of an apple or the skin on an avocado or something like that. That's about how big the crust is in comparison to the Earth, the whole Earth. It's just very, very small. In fact, it's less than 1% of the weight of the Earth. Just this little thin, paper-thin crust, okay? It is relatively less dense, stony material, okay? Relatively, I could say, not so dense, stony material. I can actually get a little sample of it for you to show you kind of what's representative of the crust. Okay, so here it is, and this is actually just a piece of vesicular basalt, and it gives you a pretty good idea of this, what the crust is made out of. Rocky material, but it's, even though this seems really dense, it's actually relatively light compared to the rest of the material of the Earth. And I mean, has a relatively lower density. You're going to see one thing about the Earth is that it gets denser and denser as you go deeper and deeper and deeper into it. And that should make perfect sense because that's gravity, right? That's buoyancy. Things that are denser tend to sink. Things that are not so dense, they're more buoyant, tend to rise, okay? Makes perfect sense. And of course, the least dense material is on the very surface, okay? Now, we're going to keep on moving down. We have the big boy of the Earth. That's the mantle. That's this chunk, this green material that I showed you right here. The mantle is green, and it's actually really beautiful. If you could actually hold this piece and look at it, you'd probably be amazed at how pretty this is. Believe it or not, a lot of people, it's hard for them to comprehend this. Do any of you know the birthstone peridot? I think it's August birthstone. It's a beautiful green birthstone. I like it a lot. I actually got my wife some earrings made of peridot. Look really pretty. And believe it or not, that's about 50% of what the mantle's made out of, at least the upper mantle. I think that's really cool. It's actually, imagine that, 50% of the mantle is made of a beautiful gemstone. So that's the mantle. That's the big boy. It's the you can think of it as the Texas of the Earth, okay? It is 66% of the Earth's mass. It's even more in terms of the volume of the Earth. And it's made of relatively denser, stony material. So It's absolutely solid stone. Okay. The next is the outer core. That is made of not stone, but metal, and it's a liquid metal. So these little pieces that I showed you of the core, these are obviously solid, but at one point they might have been liquid iron, right? So they've cooled off now, thankfully, because that outer core is hot. It's about 5,000 degrees Celsius, and white hot. And it's made of iron, so it's liquid iron. Okay. And the next is, of course, the inner core, and that is solid iron. It's actually an iron-nickel alloy. So these cores usually have planetary cores usually have a fair amount of nickel in them. About 5% nickel is average. So if we were to take a sample of these little pieces of the core, okay, did anybody think about where I might have gotten these yet? If you haven't figured it out yet, these are actually iron meteorites. So iron meteorites, believe it or not, find these on Earth sometimes. Iron meteorites, believe it or not, I kid you not, are the cores of planets that have exploded early in Earth's history. From their very cataclysmic early solar nebula, there were small planets and planetesimals colliding and creating tremendous explosions, blew the planets and planetesimals and small planetary bodies apart, releasing their cores, fragments of their core, I should say, into outer space. And sometimes we are on a collision course with those little fragments, and we know them as meteorites, meteoroids, right? Things like that, even asteroids. So anyway, the outer core is made of metal. So is the inner core. Outer core is liquid. Inner core is solid. So the only layer that's completely molten is the outer core. We'll talk a little bit later about how we know that. We'll talk about that a little bit towards the end of the lecture. Okay, so wait for our section on the outer core. So Earth's structure is layered, okay? We go through the crust, and it's amazing because actually if you look at this, you might not even have noticed the crust. The crust is just so thin. So this is a diagram that shows a kind of cross-section going into the Earth, okay? Starting at the surface. That's the depth, right? Depth in kilometers. You know, we do the metric system here, and we're going to be using kilometers. So the interior of the Earth, the very center of the Earth, is 6,400 kilometers depth on average. Of course, you have to remember that Earth isn't a perfect sphere. It's actually an ellipsoid. So it actually kind of depends where you're at on Earth's surface to get actually the depth to the center. But on average, it's around 6,400 kilometers deep. Now, you can see that the crust really is very, very thin. It's less than 70 kilometers thick. Okay, it's less than 70 kilometers thick. So that, number 4 says, how thick are these layers? The crust is less than 70. Now take a look at the mantle. The mantle goes boom, 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 all the way down, almost half of the radius, right? Half the radius of the Earth, all the way down to about 3,000. Probably more accurately, average is more like 2,900 kilometers. So anyway, the mantle is around 2,900 kilometers thick. Okay, like I said, it's the big boy. It's the big part of the Earth. Finally, we have the outer core and inner core. They're the other half of the radius. Now, just because they're half the radius doesn't mean that they're half the mass, okay? The mantle's 66% of the mass, and the reason is that it's that outer shell. So it's a little bit, the geometry is a little bit different, okay? So the 50% of the radius doesn't mean 50% of the mass. So mantle's 66% of the mass. The inner core is about 33% of the mass. The crust is actually less than 1% in terms of mass, okay? Outer core is liquid, inner core is solid. Take a look at the temperatures here, okay? This yellow line here is called the geotherm. That is the temperature of the Earth as you go from the surface to the center. You'll notice that, of course, it starts off really low, okay? It starts off at around, 0 degrees Celsius, 24 degrees Celsius. And by the time you get into the mantle, you're at, maybe right here, right? Let's go down. And you're already at like 1,000 degrees Celsius, right? By the time you get down to the outer core, you're really hot. You're maybe more like 4,000 degrees Celsius, okay? Really white hot. That's if you were even around the outer core at a metal that's that hot, it's way hotter than what we like smelt iron at, right? You would just be obliterated by the UV radiation that's coming off that material, okay? So it's really incredibly hot. We're not used to. This is actually close to the temperature of the surface of the sun. So it's really, really hot inside of the Earth, and that's what powers. We're going to see later powers the dynamic Earth that we live on. Okay. Here's some basic facts about the Earth. Mass is 10 to the 24 kgs. That's kind of a weird number. That's a trillion times a trillion kilograms. Okay, so there's a trillion trillions kilograms in Earth. Okay, radius, like I said, is 6,400 kilometers. Density, pay attention to density. Density is about 5.5 grams per cubic centimeter. Okay, there you go. We got the age. That's one of your first questions there on your lecture assignment. And what are the top 4 elements for the whole Earth? In the whole Earth, it's oxygen. It's actually iron is number 1. That's the core. Then we have oxygen, silicon, and magnesium. Okay, those are the top 4 for the whole Earth. We'll talk about the crust in just a little bit. Okay, so we got the basic layers of the Earth. We already talked about that. We talked about how thick those layers are. Talked about which are molten. And we talked about the composition of the core as well. And how we know that. I'm going to cover that a little bit later towards the end of the lecture, how we know. Okay. So here's a great pie diagram showing the composition of the Earth. This is the whole Earth together, okay? And you can see that we are, by far, iron is number 1 element on Earth, okay? So we are really an iron-rich planet. And all that iron, where is it? It's down below your feet in the core. It's about 3,000 kilometers deep in the core, okay? So most of the iron, vast majority of Earth's iron, down there in the core. Okay, nickel as well. You can see that nickel actually makes it onto this chart here. 2% of the Earth, 2.5% of the Earth is nickel. That's actually, maybe it doesn't sound like very much, but when you think about the crust is less than 1% of the Earth, think about the crust being made entirely, all the nickel of the Earth could make 2 of our crusts, right? It has enough mass, actually more like 3 or 4 of our crusts, okay? So we actually have quite a bit of nickel in the Earth, and that's all again in the core. All right, now this might surprise you, but the next most common element of the periodic table is actually oxygen. Now we tend to think of oxygen as a gas, but in this case, oxygen is chemically bound to other elements like silicon and magnesium, iron, and that creates a solid instead of a gas. So we have sort of oxygen in its solid form, bound chemically with other elements, and that's actually the number 2 element in the whole Earth. We have silicon coming in at number 3, magnesium coming in at number 4 at 13%. Okay. Other things that are common are calcium and aluminum. A lot of that sulfur, you'll notice there's about 2% sulfur is in the core. Okay, so a lot of this stuff we don't even think of because that stuff's in the core. We don't really notice it on our everyday lives. But the core is really important. You're going to learn a little bit later why that beautiful core is so important. You should thank the stars you have that core. Your life would be totally different without the core. So we'll talk a little bit more about that later. Let's go into the crust. Okay, so the crust is that outermost layer, less than 1% of the Earth. Its thickness varies exactly where you are. Okay, when you're over the continents, like we are here in Corpus Christi, we're relatively thick, maybe 30 kilometers thick. However, when you're over the ocean, you can see that the crust is thick over the continents, but then it thins out once you're over the ocean. So over the ocean, it's really maybe only 5 kilometers, maybe max 7 kilometers. Continental crust can get up to 70 kilometers thick, but the crust becomes sort of gravitationally unstable once you get above 70 kilometers. So you never get stuff over 70 kilometers. So that actually puts because you can imagine, where do you think we get the thickest continental crust? If you're thinking mountains, that's the correct answer. Mountain ranges are where we get the thickest crust. So mountains can really, there's like a maximum cap on how tall mountains can be. At a certain point, they gravitationally just collapse. All right, so what's the crust made out of? Now you notice you have a question near top. Was it number 2 actually, talking about abundant elements in the crust, the whole Earth and the crust. You can see that it's very similar to the whole Earth, but we still have oxygen, silicon, iron in kind of the top 4, but instead of magnesium, we have aluminum in the top 4. We also have oxygen as the number 1 element. So believe it or not, the rocky part of the crust, about 50% of it is just oxygen. It's just made of oxygen. And again, it's not the oxygen we breathe or the oxygen gas. It's oxygen chemically bound to other elements like aluminum, iron, calcium, magnesium, silicon especially. That's what the oxygen is. So about 50%, you pick up a rock, about 50% of that rock that you pick up, you're just holding oxygen. Okay, so there are your top elements. Oxygen, silicon makes an appearance now at 25%. Aluminum, iron, those are the top 4. Okay, so it's really kind of amazing, but like 90% of the crust is just 5 elements: oxygen, aluminum, silicon, iron, calcium. You throw in another 4, hydrogen, sodium, magnesium, potassium, and you got basically 99% of the crust. So even though there are 92 naturally occurring elements in the periodic table, 99% of the crust is just like 9 or 10 elements. Okay, so a lot of different kinds of elements, but some of them, in fact I should say most elements of the periodic table, they're almost all present in the crust, but the vast majority of elements in the periodic table are in very, very, very small amounts. Okay, so the crust is a majority, just those 9 that are shown up there in front of you. All right, now let's talk about 2 kinds of crust. This is really important. It's on the midterm, it's on the final. You have to know this. It comes up a lot in this class. There are 2 flavors of crust, 2 kinds of crust in 2 styles. Okay, so those kinds of crust are continental crust and ocean crust. Okay, so the crust that is that the land is made out of, and the crust that is beneath, for the most part, beneath the ocean. All right, now ocean crust is, for the most part, I find it pretty boring. It's made of this black rock. Like I have a sample of it here. It's a kind of a boring black rock. We call it basalt. Basalt's a really important rock. Personally, I find it kind of a boring rock. There's not really much to look at. It's just kind of a plain black rock. But it's the rock that Hawaii is made out of. It's the rock that most of the ocean crust is made out of. It's the rock that Iceland is made out of, and a lot of islands that are in the middle of the ocean islands, are made of basalt. Okay, so that's a picture up there, basalt to the seafloor, and you can see that the crustal rocks are going to be quite different. Okay, so the density of this crust is 3 grams per cubic centimeter. That's a lot less than the whole Earth. Remember, the whole Earth is 5.5 grams per cubic centimeter. So why the big difference? Why is the ocean crust so much lighter than the whole Earth all put together? Any ideas? Of course, I can't hear your ideas, but maybe something to think of. But if you're thinking it has something to do with the core, you would be right. Remember that the core is made out of really heavy iron. I don't know if any of you ever pick up just a piece of iron, but it's very dense, right? So that iron actually gets even denser in the core due to the very intense pressures. So anyway, continental crust is very different. It is made out of a great variety of different kinds of rocks. So that's one big difference between the continent and ocean crust. Ocean crust is relatively homogeneous. It's just basalt, blah, you're done. Continental crust is different. You have a lot of different kinds of rocks. You have rhyolite and basalt. You have limestone. You have sedimentary rocks. You have metamorphic rocks. You have marble. All these different kinds of things. But if you were to mash it all together and take an average, the average rock of the continental crust is something called diorite. It's probably a rock you never even heard of before. A lot of people would look at this and call it granite. It's not granite. In fact, if you read a lot of textbooks, they'll erroneously say it's granite. It's not granite. The average rock is dioritic, okay? It's a intermediate composition, and we'll talk more about what that means when we study igneous rocks in this class. So continental crust is less dense than ocean crust, and that's important. It's important. It's more important maybe that you realize. And you can see that the density difference is not very big. We're talking about 2.7 grams per cc, 2.7 grams per cubic centimeter versus 3 grams per cubic centimeter. So you might say, what's the big deal? It's just 0.3. But that 0.3 makes all the difference. If we had a density that was greater, we would kind of, maybe you can imagine the continental crust sort of like blocks of wood floating in water. We would actually, if these blocks of wood were heavier, what would happen? The blocks would sink deeper into the liquid. Now, the mantle is not liquid, but you'll see later that it is liquid-like, even though it is totally solid. So the crust literally does sink into the mantle and literally floats in the mantle, even though the mantle is a solid. But if it were denser, it would sink deeper, and then we would have a lot less continental crust to call home. We would be underwater, almost would be like Kevin Costner in Waterworld in that 1999, I think it was, Hollywood flop. But anyway, if you don't know what I'm talking about, that's fine. But it would be like that movie Waterworld. So anyway, continental crust is also different than oceanic crust in that we have here on the continents more silicon, more oxygen. I'm sorry, take aluminum here. I put that in by accident, and we have a more potassium as well. So the rocks are chemically different. They're less dense. The crust is thicker. It's more homogeneous. Lots and lots of differences I've given you so far. Okay, so thicker, less dense. Continental crust has more silicon, more oxygen, more sodium. Scratch that aluminum, put potassium. Okay. Oceanic crust, on the other hand, is thinner. It's more dense, and it has more magnesium and iron, and that presence of that enrichment in iron is part of what makes those, what we call ocean crust rocks, mafic rocks, more dense. Okay, so the average composition of oceanic rocks are more like basalt. The average composition of continental rocks is something called diorite. Looks a little bit like granite, but it's not granite. Okay, for the untrained eye, probably most people would look at that and call that granite, but it's for a geologist, we don't call it granite. Okay, one obvious difference too is that continental crust obviously has a higher elevation than ocean crust. Duh, right? That's why the oceans collect. I mean, that's what makes it ocean crust, right? It has a lower elevation. The ocean collects, the waters of the ocean collect there in those low elevation areas. Okay. All right, so let's move on now. That's the crust. Let's move on to the big boy, to the mantle. Okay, so we have denser stony material. Now, one important thing about the mantle is it is 100% solid. Okay, 100% solid. Well, I shouldn't say 100%. It's like 99.5% solid. But it's solid. Okay, it's solid rock. It's 2/3 versus total mass, so that's that's 66% of the mass. It's composed of stony material that's denser than the crust, even the ocean crust. So we have a density of maybe anywhere between 3.5 all the way to 5, maybe 4.5 grams per cc in the mantle. Okay, so remember 66%. Okay, like I keep repeating that number. That's on the test. It's one of the questions where you have to actually type in a number to answer it correctly. Okay, so you have to remember the actual number. It's 66%. So the mantle goes all the way down from the bottom of the crust, and we call the bottom of the crust the moho. More about that later. But we go all the way from the bottom of the crust down to 2,900 kilometers, where we go from about 600 degrees Celsius at the surface of the mantle, top of the mantle, down to 4,000 to 5,000 degrees Celsius at the bottom of the mantle. Okay, pressure at the bottom of the mantle is intense. It's about 134 gigapascals. It's a billion pascals. You might be wondering, what the heck is a pascal? A pascal is a metric system unit for measuring pressure. The standard air pressure that you experience here on the surface of Earth is about 100,000 pascals. That might sound like a lot, but compared to 134 billion, it's nothing, right? So you're actually having a pressure at the mantle, core mantle boundary, that is millions of times what we have here on the surface of Earth. Okay, like I said, the boundary between the crust and the mantle has a special name. It is properly called the Mohorovicic discontinuity. Mohorovicic was a Czech scientist. No one ever says his name anymore. We all just abbreviate it MOHO. So if you call it the MOHO, everyone knows what you're talking about. There's no reason to say Mohorovicic. But you do have to know that word, because sometimes it'll come up in lectures and things like that. I'll refer to the MOHO. You have to just know that's the mantle crustal boundary. Okay. So anyway, one of the most important facts about the mantle, and this is the reason I bring my beautiful lava lamp here. It's not just for ambiance. It's actually to remind you of something real that's going on in the Earth. The most important fact of the mantle, and I do hope you're paying attention right now, the most important fact is that despite it being solid, it is able to convect like a liquid, much like a lava lamp. I bring this because I want people to make the connection here. Think of the mantle as a lava lamp. Now you know what a lava lamp does. It has heat from the bottom, right? You have this nice little lamp here at the bottom. It keeps the wax here warm. And as it melts, right? Now there's no melting, or not much melting in the mantle, but when it gets sufficiently hot, the wax starts to rise, okay? And then it will buoyantly rise until it reaches the top. And of course, the top is kept cool. So now that wax is going to cool down, it's going to go back down. Same exact thing happens to Earth. The core, is 4,000 to 5,000 degrees Celsius. The top of the mantle is still very hot, but relatively cold compared to the bottom, 600 degrees Celsius. So that material at the bottom becomes buoyant. It wants to rise, while the material at the top becomes dense and cold, and it wants to sink. That creates convective cycles, and that's what powers the convection of the mantle. That's what powers plate tectonics, when we talk about that a little bit later. So this is solid state convection. The mantle is not a liquid, but it can exhibit liquid-like behavior over time. So this little GIF video animation that you're looking at, mantle obviously doesn't move this fast. If it did, it would be a crazy roller coaster ride to live on the surface of the Earth. No, this represents more like perhaps 70 million years of Earth history that you're watching in just a couple seconds, okay? So yes, it convects, but it moves very slowly. The speed is about equivalent to to the speed your fingernails grow. So that's about how fast things move in the mantle. Well, this got all messed up. I'm sorry here. Let me whoops, change that. What needs to happen here? We need to maybe make this a little bit longer. There we go. Okay, now it looks good. So we need to get into this important distinction in the mantle. It's called the distinction between the lithosphere and the asthenosphere. And I do believe I have some questions about that, at least on the back page, about the lithosphere and asthenosphere. So the lithosphere is the solid part of the Earth that consists of the crust and uppermost mantle. it is solid and it behaves the way that you are used to in a rock. You know, if I take this rock and I try to pull it apart, it would just crumble and break if I had the strength. Of course I don't. I can't pull it apart. But you know, if I try to squeeze this or deform it, what's going to happen? This rock's going to break and crumble like a cookie. Compare that now to the mantle asthenosphere. The mantle asthenosphere is the part of the mantle that does not break like a cookie. It is the part of the mantle that can convect. It is sufficiently warm and under sufficient pressure to change its, I can say, malleability or its mechanical properties. And instead of cracking and crumbling and breaking like a cookie, like we're used to with rocks, it actually can deform, bend, fold, convect, and do all those things. Maybe think more of cookie dough. So if the lithosphere is the cookie, the asthenosphere below it is the cookie dough. So cookie dough, you know, you can mold it, bend it, shape it. It's a plastic material rather than an elastic material. Okay, so that's the difference between lithosphere and asthenosphere. It's a mechanical difference. Now, the lithosphere is colder than the asthenosphere, but that's not the important distinction, the essential primary difference. The essential primary difference is that the asthenosphere is has different mechanical properties. Okay. All right, now let's move on to the core. Really important thing about the core. So the outer core, it's made of iron. Of course, it's made of liquid iron. Now, of course, I don't have any liquid iron here for you to show you, because that would be incredibly hot. But I do want to remind you of something. Perhaps you've seen this experiment before. It's kind of a neat experiment. Sometimes they do this in grade school. But what I have here is a copper coil. Okay, that's a copper coil. All right, conducts electricity really well. And what I'm going to do is I'm going to put that over a rod of iron, a metal iron rod. Iron, just like what our core is made out of. Now, what I also have here is I also have a get myself all tongue-tied. An electrical source. Electrical source. Why am I having a hard time saying that? Okay, so I have an electrical source right here. I'm going to turn it on now. Is it on? Oh, I have to plug it in. I didn't plug it in. So let me plug it in here. And I got to unplug my coffee machine. Plug this in. Okay, so it's plugged in. You can see the power is on now. And here are the alligator clips. And this is what I'm going to do. Now, you can see I have this rod of iron and I have some paper clips here. And if I go like this, you'll notice I obviously don't lift any paper clips out, right? I can't pick up any paper clips, okay? And that makes sense. This iron is not magnetic, okay? It's susceptible to being magnetized, but it's not magnetic itself. Now, where'd my little coil go? Lost my coil. Where'd I put it? Okay, here it is. So I'm going to take my coil and I'm going to put it on my rod like that. Okay, you see that? So now I have a coil, copper coil, and now I'm going to hook up the electricity. Okay, so there's the first alligator clip on there, and I'm going to get my second one on here. Okay, you can probably see the sparking right there if I do that. So we now have put some electrical current through this. So now what's happening is that we have an electrical current that is spinning around, spinning, flowing in this coil around the iron. So we have a spinning, circulating electrical charge. And you can see now I can stick this into the paperclip box and pick up all sorts of paper clips. And that's because I've magnetized my iron rod. Okay, so what does that show us? It shows us that when you have circulating iron, it can create an electrical current circulating in the iron. It can induce and create a magnetic field. And that's exactly what's happening in the outer core. We have the outer core, Circulating and convecting. Yes, there is convection in the outer core, and it is also circulating along with the rotation of the Earth in its daily 24-hour rotations, and that creates a magnetic field, right? So the circulating iron has an electrical field that induces a perpendicular magnetic field. Okay, and that's so important. That magnetic field, whether you realize it or not, is absolutely required for life on Earth. That magnetic field blocks out the extremely hazardous solar winds and some of the worst kinds of solar radiation. You have to remember, a lot of nasty stuff comes out of the sun. Very powerful ionizing radiation. And we're protected from it by the outer core. And guess what? When those solar winds that are so dangerous and hazardous encounter the magnetic field, what does it create? It creates the aurora borealis, or the aurora australis in Australia, in the southern hemisphere. It creates this beautiful light show in the sky. And that's literally, it's protecting us. So you maybe never thought about the core before in your life, but now is a good time to start thinking about it, because your life depends on the core. One of the big challenges for people scientists who want to try to terraform Mars or make Mars inhabitable, one of the big challenges is that Mars doesn't have a magnetic field. So if we were to want to live there, humans would want to live there, we would need to create some kind of a magnetic shield or some kind of a artificial magnetic field to protect us from the sun's very hazardous solar radiation. Okay. Now, how do we know that the outer core, that was one of the questions in the beginning in your lecture assignment, how do we know the outer core is a liquid? We actually know that all that information about the inside of the Earth, almost, not all of it, but a lot of it, comes from earthquakes, comes from seismic disturbances. What do I mean by that? Well, when an earthquake occurs, it creates seismic waves. Those are just acoustic mechanical waves, like sound waves, like ultrasonic waves. You know that we can use ultrasonic waves to look at what's going on inside of a person's body, for instance. So, you know, when you're pregnant, the ladies go in and they get an ultrasound. You can see the baby inside the womb using ultrasonic acoustic waves. And you can probe and look inside what's going on inside your body. Of course, they're not only for pregnancy, but they use it for different medical conditions. They can visualize different things that are going on in your body with ultrasonic acoustic waves. Okay, same thing. I think of earthquakes as an ultrasound for the Earth. Those acoustic waves that are created, mechanical waves, seismic waves that are created by the earthquakes, are able to be detected by seismographs all over the world. We have a whole incredible network of seismometers that are stationed all over the world, and we can visualize three-dimensionally what's going on inside of the Earth. And we can also figure out that the outer core is there, and it's also, we know its depth, and we also know that it's a liquid because certain kinds of waves seismic waves can propagate through liquids and certain kinds cannot. And the ones that cannot propagate through a liquid, called S waves, do not go through the outer core. So that's how we know it is a liquid, and we know that the inner core is a solid. To wrap things up, the inner core, I don't have much to say about it. It's not as exciting, but it is a solid piece of iron right in the center, and goes from 5,000 kilometers to 6,400 kilometers. That's the thickness of that layer, so it's about 1,400 kilometers thick. Let me just make sure I hit everything here. I think I did. I just want to give you a little bit of advice. You can see number 15, okay? You have to draw a picture. Now, I just want to give you some advice. When you do this, let me actually pull this up in front of your screen so you can see this yourself, okay? So this is your lecture assignment, right? When you draw this, notice that I'm only asking for the top 100 kilometers of the Earth, okay? How thick is the Earth? 6,400 kilometers. So if you draw this, and so many students do, they draw like a hemisphere of the Earth, and they draw the core. You're showing me 6,400 kilometers of thickness. I only want this. Not even that. 100 kilometers up here. That's all I'm asking for. Because you can't properly show the continental crust. If you were to draw things like this, you couldn't show the continental crust or the ocean crust. You can't show 5 kilometers thickness on there. Okay? So you need to draw something that looks more like, let me show you kind of what to draw. You should draw something more like this. This diagram is kind of more on par with what you should be depicting there. Okay, that's about 100 kilometers of thickness. And you notice how that has the asthenosphere and the lithosphere and all that. Okay, notice you have some questions from your reading as well. All right, you do have a few questions there from the reading. It's in there. I'm pretty sure it's in the book. I know they changed editions recently, but I checked that new edition and it's still in there. So it's to my knowledge, it's at, let me get it right now and give you some help. Here's your book right here. I think this is the edition that you use. Or maybe not. This is 7th edition. You guys might be on 6th. I can't remember. But anyway, I think it's in, yes. It is in chapter 7. Let me just show you in case you're interested. Oh no, not chapter 7, chapter 9. I'm sorry, I'm confusing you so much. Chapter 9. So it's this stuff, it looks like it's this section that looks like that, you can see, and it's got all that interior of the Earth. Okay, so read that and you'll find most of the answers there. Okay, so anyway, that's it for the lecture for today. Hope you enjoyed this one, and I will talk to you next time. And did you all come up with an answer for how do we get samples like this? How do we get a piece of the mantle? In case you were wondering, it's from volcanism. Okay, so volcanoes often originate, the liquid originates in the mantle, comes up to the surface, and it brings hunks of the mantle along with it. And so hope you got a chance to think about that question a little bit. Okay, so I will catch you later, and you have a great day, great week, and talk to you next time.